Dear students, after studying this module, you shall be able to know how to make samples for recording the spectra of different organic compounds, understand the working of IR Spectra Photometer, and have an hands-on experience of recording the IR spectrum. Sample preparation in IR spectroscopy. Dear students, now we will tell you how do we record a sample in infrared spectroscopy. IR spectrum of a compound can be recorded in many different forms such as liquid, solid, gaseous and in solution state. Some of the materials are opaque to infrared radiation. So, in order to obtain spectra, they must be dissolved or diluted in a transparent matrix. For recording IR spectra, the sample should be properly dry as water absorbs near 3710 and 1630 centimeter inverse. The samples should be perfectly dried since cell materials like sodium chloride and potassium bromide are usually spoiled by moisture. Solid samples. There are several methods by which an IR spectrum of a solid sample can be recorded. Now we look into each of these methods in detail. First is as a pressed disc. The first common method involves the mixing of finely ground solid sample with powdered potassium bromide. A translucent pellet of this powder mixture is formed by pressing under mechanical pressure. The main advantage of using potassium bromide is that it does not interfere with the bands due to the compound, since potassium bromide is transparent to IR radiations in the range of 4000 to 650 centimeter inverse, and this range is useful for an organic chemist, and thus it gives a better spectra. The disadvantage of this method is that potassium bromide absorbs water very quickly, which may interfere with the spectra that is to be obtained. Now, the second method to obtain a solid sample is as a mull or a paste. Finely ground compound is mixed with an oily mulling agent, usually known as nujol, using a pestle and a mortar. A thin film of this mull is placed between two flat plates of sodium chloride and the spectrum is thus recorded. The main disadvantages of this method is that nujol has absorption bands at 2924 to 2860, 1462 and 1380 centimeter inverse. So, these are the interfering bands in our interesting region. Therefore, no information about the observed compound can be obtained in this region. Third is preparation of solid sample as a film. A third method is to dissolve the solid sample in a suitable non-hygroscopic solvent, usually methylene chloride or carbon tetrachloride. A drop of this solution is deposited on the surface of potassium bromide or sodium chloride plates. The solution is then evaporated to dryness and the film is thus recorded on the potassium bromide disc and analyzed directly to obtain the IR spectrum. The most important thing is that the film should not be too thick, otherwise light will not be able to pass through it. This method gives good results with dilute solution of the compound in a non-polar solvent. Second, we come on to the liquid sample preparation. Liquids are studied neat or in solution. A drop of neat liquid sample or a solution of the sample in an appropriate solvent is placed between the two plates of a salt, generally sodium chloride or potassium bromide, to give a thin film and analyze to obtain the spectrum directly. The plates are transparent to the infrared light and do not introduce any lines onto the spectra. Salt plates break easily and are water soluble. Therefore, compounds analyzed by this method should be free from water. Spectrum obtained by this method is known as neat spectrum since no solvent is used in recording the spectrum. We now come to the preparation of gaseous samples. The gas is introduced into a special cell with a long path length, and the walls of its both the ends are normally made up of sodium chloride. Gases have very less densities compared to liquids, and hence path lengths should be correspondingly greater, usually 10 cm or longer. The vapor phase technique is limited because most of the organic compounds have very low vapor pressure to produce a useful absorption spectrum. It is important here to note that the spectra obtained from different sample preparation methods will look slightly different from each other due to differences in the sample's physical states. Now we come on to the instrument of infrared spectroscopy, that is the Ir Spectra Photometer. Traditionally, dispersive infrared spectrophotometers developed in 1940s were used to obtain the infrared spectra. In 1960s, a new method was developed known as Fourier transform infrared, that is FTIR spectrometer. But due to high cost of the instrument, this was tended to be used for advanced research only at that time. Gradually, technology advancements in computers and instruments have reduced the cost and enhanced the capabilities of FTIR spectrophotometer. Today, they are predominantly used and have improved the acquisition of infrared spectra dramatically. Next is we come to the dispersive infrared spectrometer. The basic components of dispersive IR spectrometer includes a radiation source, sample and reference cells, monochromator, detector, amplifier and recorder. A schematic diagram of a typical dispersive spectrometer is shown in the figure. We now discuss in detail the various instrumental parts of the dispersive spectrophotometer. First being the radiation source. The common IR radiation source are inert solids that are heated electrically to a range of 1000 to 1800 degrees Celsius to promote the thermal emission of radiation in the infrared region of the electromagnetic spectrum. The most common sources are the nursed filament, which comprises of rare earth oxides such as zirconium, cerium and thorium, globar composed of silicon carbide and nichrome coil. They all produce continuous radiations but with different radiation energy profiles. The beam from the source is divided into two equivalent beams, one passing through the sample and other as a reference beam. Sample and the reference cell, which are the next part of the instrument, like UV sample tubes known as cuvettes, glass or quartz cannot be used to make the sample cells for IR spectroscopy because they absorb strongly in the most of the IR region. Alkali metal halides such as potassium chloride and sodium chloride are commonly used as they are transparent to the infrared region, as discussed before too. The next part of the instrument is a monochromator. The monochromator is a device used to disperse or separate a broad spectrum of IR radiation into a continuous spectrum of frequencies of infrared light. The monochromator consists of a rapidly rotating chopper that passes the two beams alternately to a diffraction grating. The slowly rotating diffraction grating varies the frequency or wavelength of radiation, sends it to the individual frequency to the thermocouple detector, which generates an electrical signal as a response. The next parts are the detectors and the amplifier. The detectors are devices that convert the radiant energy into an electrical signal. The detector determines the ratio between the intensities of the reference and sample beams. Due to the difference in intensities of the two beams falling on the detector, an alternating current starts flowing from the detector to the amplifier, where it is amplified and relayed to the recorder. The detectors used in IR spectrometers can be categorized into two classes. One is the thermal detectors and the other is the photon detectors. Thermal detectors consist of several thermocouples connected together to produce greater sensitivity. They measure the heating effect produced by infrared radiation that causes the flow of current. The current produced is proportional to the intensity of radiation falling on the thermal detector. Photon detectors, on the other hand, rely on the interaction of IR radiation and a semiconductor material. Non-conducting electrons are excited to a conducting state and therefore producing a small current or voltage. The next part is the recorder. It records IR spectrum as a plot of frequency of absorbed radiation and intensity of absorption in terms of transmittance. Unlike UV spectroscopy, here we use the wave number unit. As the detector records the ratio of the intensities of the two beams, therefore percent transmittance is recorded as transmittance T is equal to I divided by I naught. Percent transmittance, that is percent T, is equal to I divided by I naught multiplied by 100, where I naught corresponds to the intensity of the incident radiation and I is the intensity of the radiation emerging from the sample. This is clearly depicted in the figure that you can see. We can see the IR source, the sample compartment, the reference and the sample cells, the chopper, the detector and the monochromator clearly in this figure. Now next we come on to the second type of infrared spectrophotometers, that is the Ftir or the Fourier transform infrared spectrometers. Fourier transform spectrometers have recently replaced dispersive instruments for most applications due to their superior speed and sensitivity. They have greatly extended the capabilities of infrared spectroscopy and have been applied to many areas that are very difficult or nearly impossible to analyze by dispersive instruments. Instead of viewing each component frequency sequentially as understood in a dispersive infrared spectrometer, all frequencies are examined simultaneously in Fourier transform infrared spectroscopy. The basic components of an Ftir spectrometer are shown schematically in figure as you can see. The radiation emerging from the source is passed through an interferometer to the sample before reaching a detector. Then the signal is amplified and converted to digital form by an analog to digital converter and transferred to the computer in which Fourier transform is carried out. Interferometer divides radiant beams, generates an optical path difference between the beams and then recombines them in order to produce repetitive interference signals measured as a function of optical path difference by a detector. Thus, an interferometer produces interference signals which contain infrared spectral information generated after passing through a sample. The most commonly used interferometer is a Mitchellson Interferometer. It consists of 3 active components, which are a moving mirror, a fixed mirror and a beam splitter. This can be easily seen in this figure. The 2 mirrors are perpendicular to each other, that is at 90 degrees to each other. The beam splitter is a semi-reflecting device and bisects the plane of these 2 mirrors. The beam splitter is often made by a coating of thin film of germanium or iron oxide into an infrared transparent substrate such as potassium bromide or cesium iodide. The energy goes from the source to the beam splitter, which splits the beam into 2 parts. One part is transmitted to a moving mirror, one part is reflected to a fixed mirror. The moving mirror moves back and forth at a constant velocity. The 2 beams are reflected from the mirrors and recombined at the beam splitter. The beam from the moving mirror has travelled a different distance than the beam from the fixed mirror. When the beams are combined, an interference pattern is created. Some of the wavelengths recombine constructively and some destructively. This interference pattern is called an interferogram. This interferogram then goes from the beam splitter to the sample, where some energy is absorbed and some is transmitted. The transmitted portion reaches the detector. The detector reads this information about every wavelength in the infrared region simultaneously at the same time. This is clearly depicted by the figure that you can see here. Now, the moving mirror produces an optical path difference between the 2 arms of the interferometer, the relative position of the moving mirror to the fixed mirror. If the 2 mirrors are an equal distance from the beam splitter, the 2 beams travel the same path length. Therefore, 2 beams are totally in phase with each other and hence they interfere constructively and lead to a maximum intensity reaching to the detector. When the moving mirror travels in either direction by a distance of lambda divided by 4, the optical path is changed by 2 into brackets lambda divided by 4 bracket closed, or in other words lambda divided by 2. The 2 beams are 180 degree out of phase with each other and thus interferes destructively, resulting in minimum intensity which reaches the detector. If the moving mirror further travels by lambda divided by 4, then the optical path difference will be lambda, that is 2 into lambda divided by 2, which becomes lambda. The 2 beams are again in phase with each other and result in constructive interference again, giving a maximum response in the detector. Such a maximum will be observed when the path difference is an integral multiple of lambda. Thus, moving mirror is the key component of an interferometer because alternate light and dark images will reach the detector if the mirror is slowly moved away either from or towards the beam splitter. When the mirror is moved at a constant velocity, the intensity of radiation reaching the detector varies in a sinusoidal manner to produce interferogram. The interferogram is a complex signal, but its wave-like pattern contains all the frequencies that make up the infrared spectrum. It is actually a time domain spectrum and records the detector response versus time. If the sample happens to absorb in this frequency, the amplitude of the sinusoidal wave is recorded by an amount proportional to the amount of sample in the beam. Now students, to obtain the infrared spectrum, the detector signal is sent to the computer, where mathematical operation known as Fourier transform converts this interferogram, that is a time domain spectrum displaying intensity versus time, to the final IR spectrum, a frequency domain spectrum showing plot between intensity of signal versus frequency. Now students, after having learnt about the two type of instruments of IR spectroscopy and sample preparation, we now lead you to the hands-on operation of an Ftir spectrometer, which is nowadays used commonly in all of the laboratories. Step 1. First step is the sample preparation. Sample preparation has already been discussed in the above section by me. Step 2. The second step is to obtain an interferogram of the background, which consists of an IR active atmospheric gases like carbon dioxide, which shows a doublet at 2360 cm inverse and a sharp spike at 667 cm inverse. This phenomena has been discussed in the earlier modules, why CO2 shows such band sharp spikes. This is again the spectra is shown in the figure, and the spectra of water vapors which is in the background, which shows two irregular groups of lines at about 3600 cm inverse and about 1600 cm inverse. This again is shown in figure. Nitrogen and oxygen are not IR active, and hence even though being as atmosphere gases, they do not absorb in the IR region. This interferogram is subjected to Fourier transform, which gives the spectrum of the background. Now step 3. In the third step, spectrum of the sample under investigation is obtained by the similar procedure. This spectrum contains absorption bands from the sample as well as the background, whether gaseous or solvent. Step 4. The ratio between the single beam sample spectrum and the single beam background spectrum gives the spectrum of the sample. Computer software automatically subtracts the spectrum of the background from the sample spectrum. Now step number 5, which is the final step. Finally, the data obtained is analyzed by assigning the observed absorption frequency bands in the sample spectrum to appropriate normal modes of vibration in the molecules. Now students, we summarize whatever we have learned in this module. The IR spectrum can be obtained in all three states, that is solid, liquid, gaseous, as well as in liquid solution. The Fourier transform infrared spectrometers are superior to traditional dispersive spectrometers and give high resolution spectrum in less time. So these are the two things that we have learned in detail in today's module.